Alright, so I want to go over ODP 208. I want to talk about some more details of building these nodes for a linked list in memory and tying them together. And then I want to talk about variations on a linked list, getting rid of the sentinel, doubly linked lists, circular lists, and then move on to hashes. So any questions before we get started on all that? Yeah?
I noticed there wasn't an ODP listed.
You are correct. There was not an ODP today. I think I will post one for tomorrow, which will touch on linked lists without sentinel nodes, which isn't really any different, but I'll post one tomorrow morning. And we're probably going to phase out of linked lists after today. So, and I may put some hash ODPs together and post those. All right, so let's talk about 208. So you remember the setup. You're writing a function build that takes 3 integers, builds 3 nodes with those values, and then creates a sentinel, chains them all together in a list, and returns the address of the sentinel. So let's look at some code. So you've got to include standard lib when you're using malloc. You want to include standard IO when you're using null. So I got both of those in there. And in general, these don't do any harm, but if you don't need something from there, don't include them. If you've got a function that's calculating a square root and is doing a bunch of assignments and stuff like that, but doesn't do any IO and doesn't use null, you don't need standard IO. You don't need standard lib if you're not doing freeze and mallocs or other things like that. You do have to tell it what a struct node is. So I've got struct node definition, and then here's the build function. And I decided to make 4 different variables, each pointing to a struct node, just so I didn't have to think too deeply on how to do this. So I've got 4 struct node stars. I pass each of them to malloc to have them point to some particular location in memory. And then I set the data fields on my 3 nodes, 1, 2, and 3, to be x, y, and z. And then I set up the links from one node to the next. So sentinel points to n1, n1 to n2, and so on, and n3 points to null. And the effect is you end up with a good old linked list like this. And I'm going to draw this like that. So moving away from the split boxes. So 3 data nodes, n1, 2, 3, and a sentinel pointing to the first, and they just chain together. And then we return sent, which means we're returning the address of this first node. When we get back to the caller does not have access to n1, n2, or n3. Those were temporary variables. Sent was a temporary variable, but since we returned it, the caller presumably said, you know, my sentinel node pointer equals build parentheses blah blah. And so it has a copy of what sent was. But it does not have a copy of what n1, n2, n3 were. How does it get to these nodes? It follows from the sentinel to the first node, follows from there to the second, and from there to the third. So here's the main program. So it declares a struct node. It declares a prototype for the build function. And this main program just does random things. It takes 3 arguments from the command line, which are the 3 values of x, y, z I want to put into the list. And it calls your build function. Passes x, y, and z, takes the return from the build function, stores that in this struct node pointer called sent. And now I should be able to print out sent arrow next arrow data. Well, this is sent. Sent arrow next is n1. Sent arrow next arrow data should be x. So this should print out 4 times whatever value x was. The next line will print out 7 times whatever the value of y was, and then it prints out 11 times the value of z. And then it prints out what the sentinel points to, what that points to, what that points to, what that points to, which is basically what N3 is pointing to, which should be null. So that's how a typical calling program might use the return.
So the %lx is not reprints null, or is that?
%lx prints out a long integer.
Oh. Okay.
And I'm printing it out in hex, so it'll print out 8 bytes. And I don't know what this actually does. Let's try it. Main 208, 1, 2, 3. So it just prints out a 0. There's a way to print a pointer. It might be %p, yeah. And I think that might actually print the word null if it sees a 0. So in this build function, anything wrong with doing that? Setting the links and then the data? No, that's perfectly fine. We've got 2 things here. We've got sent, n1, n2, n3. Those are pointers to memory. And then we've got the fields that we're dereferencing with the arrows. But those are just assignment statements. Makes no difference what order I do those in. What if I do this? If I move my n1 equals malloc statement further down in my code, is this going to work?
I think so.
So what's the problem with it? I saw people shaking their heads no.
You never said what n1 points to.
Yes. So this statement right before, when we say sent next equals n1, we don't know what the value of n1 is yet. So when we say sent next equals n1, this is pointing somewhere crazy in memory, probably null, but certainly not to our first data node. In our next statement, we say n1 equals malloc. Now n1 is equal to the address of a new node. But that's absolutely not going to change where this is pointing, because this has nothing to do with n1. This is just sent arrow next. And unless we say sent arrow next equals something, this is not going to change. So the order will definitely matter with respect to using the address of these nodes. But as long as we have n1 having a good value, we can go ahead and point to it.
So it's basically remembering to malloc before you assign.
Remember to malloc before you use that variable in any way, shape, or form. All right. So questions on this? So I used 4 variables here, one for the sentinel, one for each of the 3 data nodes. That's not necessary. Okay, I did it here, but it kind of gives the illusion that if I wanted 10 nodes, I would have to have 10 variables, A, B, C, D, E, F, G, H, I, J, and set them each equal to malloc and so on. In fact, that's not the case. So let's let's get rid of this. So let's write some code. And let's stick with struct nodes. Alright, so we'll make a single sentinel node with our malloc. And let's make a bunch of nodes and string them all together. So here's what we're going to do. So we'll put a magic flag in the Sentinel's data field, just so we can tell we're looking at the Sentinel. So we'll set that to 42. And temp is going to point to the Sentinel originally. And let's go into a loop. So we'll loop 100 times. And here's what we're going to do. Temp arrow next equals malloc. And then I'll change temp to be that new node. And then I'll set its data field. And I'll just store I squared. And that's my whole loop. So 100 times we're doing the following. We're going to set temp next to be an address of a new node. And then we're going to set temp equal to that new node, and we're going to set its data field to an interesting number. Now I only have two variables in this program, Sentinel and temp, and Sentinel never changes. So temp's the only thing that's ever changing, but somehow I'm creating 100 nodes and I'm linking them all together. And so the appearance in memory is I've got my Sentinel, which is a 42, and that's going to point to, I'll switch in a sec, thanks. So temp is going to keep changing. Sentinel is the original node with a 42. So that's going to point to a 0 and a 1 and a 4 and a 9 all the way up to 99 squared. And when I'm done with this whole loop, temp will be this last node. I don't have a variable pointing to this or that or this, but I can still get to those nodes because I have something pointing to this first node. And from there I can get to the second, and I can get to the third and the fourth and all the way up to the last one. And in fact I can get rid of temp completely. And we can still get to all the nodes. So let's call a print routine. So we'll call a function print, and that'll be the end of our program. So let's prototype this. So print takes a struct node star, it doesn't return anything. So I'm not going to write a print function right now. I'm just going to use GDB, and I'm going to stop inside the print function, and we'll look at what the Sentinel looks like. All right, so we're constructing a linked list of 100 nodes up in the top, and then we're going to pass that to the print function. So let's compile that with a G switch. Without syntax errors. Let's go into GDB, and we'll say break at the print function and run. So we're inside print now, and we were passed an argument s. That's the Sentinel. If we print it, it's a memory location. If we print star s, it's a struct node. Has a data of 42, has a next field, which is somewhere in memory. So s is this Sentinel. Okay, this is S. How do we find this node? S arrow next, exactly. So if I print S arrow next, that's the address in memory where that next node is located. Now I can examine that. That's not much fun. But I can use the X instruction, and I can see there's a 0 stored there. Well, that's not very satisfying. And there's a space filler, and here's something that looks like an address after that. But let's not do this. We know that S arrow next is this node. How do I get to this node? How do I get to any node's data field? Say again? Yeah, do an arrow data. So if I say S arrow next arrow data, that's going to give me the data value of this node. That's a 0. That's also not very satisfying. But how do I get to a node's next node? I say arrow next, right? Well, if this is S arrow next, then this should be S arrow next, arrow next. And the data value should be this node, S arrow next, arrow next, arrow data. So if I print out S next data, thanks. There's my 1. And you can see the pattern. So if I print out that node's next node and I print out the data of that, there's our 4. And if I print out that node's next node and the data of that node, there's our 9. And as long as you compile with a -G switch all your code and you link it together with -G, you can use this kind of print statement inside GDB, and it's really, really convenient. And if I want to know what the address of the node after that is, I can print out that. And if I examine that location in memory, right, there's our 16, 10 hex. So as you're going through your program, executing it line by line, comparing it to your source, comparing it to your algorithm, and you're thinking, okay, so temp should now be pointing to this node. What's its data? You can say print temp arrow data. And you can say, well, the node after that should be such and such, and you can say print temp arrow next arrow data and see what the data is in the following node, and so on. And this is really useful. This will be really, really useful when we're doing trees. Yeah?
So you compile with -G.
Mm-hmm.
How do you stop at like a function?
So before you start running your program, you can say break space. You can put in the name of a function. You can put in a line number from the listing. And then when you run or continue, it'll stop when it gets to that point. So I said break print, and that created one breakpoint at line 35, which is where my print function starts. I defined print at line 32, but the first thing it's going to do is that assignment statement at line 35. So that's where I put the breakpoint. So keep working with GDB, get more comfortable with it, and use it with these kinds of things. Because, like I say, when we get to trees, you definitely want to be able to explore your structures internally. And GDB makes it pretty straightforward. All right, let's write a print function, though. So I'm going to use T. This is how I'm thinking of this. I'm going to use T to represent the current data node that I want to print. Okay, this is my approach to this. So I really want T to start off with the thing the sentinel points to. So T is the node we're about to print. So I can do this as long as T is not null. If I move to the node after a current node and I ended up with T being null, I don't have a node. I fell off the end of the list. That's where I should exit. So if T is not null, let's go ahead and print. And we'll just print T arrow data. And then we'll move down to the next node. And there's our print loop. And then we'll just put a new line at the end. And there's our print function. And again, one temporary variable, T. But we're going to travel through 100 different nodes, 101 if we count the sentinel. And we're going to keep reusing that variable. So there's our list of data.
You printed current node data?
I printed T arrow data. Yeah, so T is my current node. So I mentioned last week there's sort of three pieces to something like this. There's initialization, which in this case was T equals S arrow next. There's the condition that you're looping on, which was T not null. And then there's what you want to do at the end of the loop, which in this case was nothing, except print the new line. And those three things are all tightly tied to each other, but there's multiple ways you can do those. So for me, I think of my variable as being the thing that I'm working with. Okay, that's just where my brain was when I first internalized this stuff way back when. Different people will have different ways of thinking about this. And it will make your code look different from someone else's code. And that's not better, it's not worse, it's not wrong, right? It's going to be individual. So let's look at a different way that we might do this. I'm thinking of t as the node that we're about to print. Let me think of it like this. T is the node we just finished with. So I'm going to start off with t equal to the sentinel. And in my loop, I'm always going to print the thing after t. So I'm going to do the following. I'm going to print the thing after t's data, and then I got to move down to the next node. And that's not too bad, except your seg fault. Let me see if we can make this more interesting. So I'm just going to call f flush, because printf is buffered output. It doesn't always print as soon as you say printf. It's actually going to save everything up until it sees a new line, but I'm going to try to force it to print each time that we call print by saying f flush. I may get in more trouble this way. Oh, there we go. So you can see it actually did print all the nodes in the list. It got down to the 9801, which is our last node, and then it got a seg fault. Okay, that's a bit of a red herring, because if you don't do that f flush, you might think it's not printing the first node and it's seg faulting right away. So even if I ask you to print everything on one line, printing things on separate lines takes care of that buffering, or doing a flush. So why is the seg faulting on the last, after the last node? Well, it's because the way that I set this up, I was thinking of t as the node that we just finished with, and my termination condition is saying, did we just finish printing the null node? And that's kind of nonsensical, because if t was null, this would have failed when we did t arrow next arrow data. So what do we really want to do? We probably want to see if t next is going to be null, because we're trying to get the data field of whatever comes after t. So if nothing comes after t, that's when we want to exit our loop. So this will cure the seg fault, and we're back in business. I thought we'd be missing a number at the end.
It doesn't print the
No,
number.
we're right. It's not supposed to, because we only went up to 99.
It breaks. I think it's 100.
Yeah, we only loaded values up to 99 squared, so that's all right. So this works perfectly fine. To me, I have to sort of really work my brain to make sense out of this print function. To somebody else, this is perfectly logical, right? It's KVL, KCL all over again. Most people, KVL feels pretty good. KCL is like, I don't get this. But there's some people, probably about 20%, who are like, KCL makes perfect sense. I don't understand KVL at all, right? Sum of product, product of sums, same thing, right? It's just different ways that our brains are wired. And whatever makes sense to you, that's the way to do it. Okay, so I'm doing it one way to try to be consistent, and I'm doing it the way that works for me. But there's other ways to do it. Now you could also, we could do t equals t arrow next up in the beginning here. And we could do this as long as t arrow next is not null. But we're back to our seg fault. And why are we segfaulting? Well, we checked to see if T arrow next was null, but then we move T to the following node, and then we pick off that following node's data. So we really, if we're going to do this, we want to see if that's the case. And that's great. But if the list is empty, that'll actually segfault. So different ways to do this, right? Find a way that makes sense for you. Don't just take my code or someone else's code or code from Google and say, well, I guess this is how I traverse a linked list, right? Find a way that makes sense to you. Go back to your pictures and work through your code and see what it's doing. And if you don't like what it's doing, have it do something different, right? There are a lot of ways to wire this up. And once you find a way that works for you, right, you'll internalize that really quickly. And that will affect how you do lists, but also trees and tries and AVL trees and all kinds of things. And it'll serve you well. Okay, so questions on that? So let's just talk about some variations on the lists. And I'm going to try to brush sentinels under the rug here, because I don't have good answers for the questions you're going to ask. So let's just think of a simple list. Well, we still have to talk about getting rid of the sentinels, but so let's just think of a list for data nodes. Okay. Oh, thanks. 4 data nodes, and this last node points to null. So null is a flag to us indicating we're at the end of the list. It doesn't go anywhere, right? It tells us we can't go beyond the 40. But we could actually take the 40 and point it back to the 10. And that gives us a circular list. And if we just do a straight traverse routine on this, it'll run forever. It'll get to the 40 and go back to the 10 and so on. So we have to do some stuff when we're moving through the list. If we only want to move from beginning to end, we've got to note the address of the first node, and each time we follow to a new node, make sure we're not back at the beginning. And if we are, we're done. The advantage, though, is that if we want to continually go through the elements of a list, we don't have to say, okay, if the next node is null, then set it equal to this address in the beginning that we remembered. We just keep following the list, and if we go back to the beginning, we go back to the beginning. And that's useful sometimes, for example, if you're processing user jobs in a computer. So you're going to take someone's program, you're going to run it for 1/10 of a second, then you're going to take the next person's program, run that for 1/10 of a second, keep going. And when you're done with the last person's program, if that first person's program needs to run some more, you'll go back and run their program. Now you run the second person's program and it finishes, so you don't have to run that program anymore, you go on to the third. You can manage all of that in a nice circular list. When somebody requests a job, you basically add them to the end of the list. When a job finishes, you delete it from the list. And every time you finish someone's job, you just move on to the next entry in the list. And if you happen to have just finished job 40, you're going to go back and rerun job 10. And so it smooths out some of these things that would be edge cases. So circular lists are handy. The other thing that's handy is a two-way list. So normally our list looks like this. So we can add a second pointer to each node that points backwards. And so this is a doubly linked list. And the struct node it's got a data piece, but then it's got 2 pointers. So it's got a next, but it might also have a previous. What's the advantage of the doubly linked list?
You can go backwards.
You can go backwards, and that's something we do a lot when we manipulate lists. For example, when you're inserting, if you want to insert a 25, we move forward until we get to the node that's bigger than 25. We want to insert before this node. We need to know what the previous node was so we can have the previous point to our new node. So we've been doing this pair of pointers, previous, current, move them forward. Here we just need to know what our current node is. Once we find that, we can look at the previous field. That'll tell us where the prior node was, and then we can touch it up accordingly. So it simplifies your coding for adds, for deletes. Makes life a little easier. The penalty is 2 struct node pointers instead of 1, so more memory. And your code gets a little more complicated. So when I want to insert a new node, let's say I want to insert a 25, well, I have to take the prior node and point to the 25, and have the 25 point to the 30. But then I also have to take 30 and have it back point to the 25, and have 25 back point to 20. So 4 pointers you have to set up instead of just 2. So a little more work, but saves you some trouble down the road. And you can have a doubly circular linked list, or circular doubly linked list, where instead of pointing to null here, we'd go back to the beginning, and here we would back point to the end of the list. And now you got all kinds of fun. Yeah.
Ooh.
So the business of having 2 struct node pointers, extra memory, you can actually get around that. So there's a trick you can do. Do you know the trick? Okay. So so this is fun to think about. You can actually set it up so that if you start at the beginning and you move forward and you get to some point and now you want to go backwards, you can do that with just a single struct node star. So you can kind of encode 2 pieces of information in one. And I'll let you think about that, but it's similar to this trick of how can you swap 2 variables without using a temporary. And you can do that by adding, or you can do it by using an XOR. And you can do the same thing here. And it's in the realm of things that unless there's a good reason to do it, I would not do it, because your code should always be as clear as possible. Right? You should not obscure your intent when you write your code, unless that's your purpose, right? If you're trying to make something as a hacking challenge or something, but unless you really, really are precious about memory, you just use 2 pointers. But it's a fun challenge to think about how would you do this with just a single pointer. And it is doable provided that you know what the node right behind you is at one point. So if you followed forward with 2 pointers, then you can keep going backwards, even though you only had 1 node back. So you can think about that if you like. All right, let me talk about the Sentinel. Because we have the Sentinel node in the beginning that that is always present and points to the first data node or points to null. But we don't have to have a Sentinel. We can do a list without that. And what does this look like? So with a Sentinel, here's a non-empty list. Here's an empty list. And in either case, the Sentinel has not changed where it's stored in memory. The only thing is, what Sentinel points to might be an address of a node, or it might be null. But Sent itself is always this block of memory here. If we don't have a Sentinel, let me put a data value in here. Here's what our non-empty list looks like. here's what our empty list looks like. It's just null. It's nothing. So sent equals null. And here there's a fundamental difference between the empty and the non-empty case. In the case of an empty list, our sentinel variable is null. In the case of a non-empty list, our sentinel variable points to a struct node in memory somewhere. Okay, what does this mean in our main program? This is how we create an empty list. And we probably wouldn't call it sent since we don't have a sentinel, so let me call it temp. Or let me call it list. Okay, so struct node star list equals null. That's an empty list. We want to add some number to that list. What do? We say add. We pass it our list, and we pass it a number. And this says add num to the list. And this cannot work because our list is originally null. When we add our number to our list, what we should do is we should end up with a block of memory somewhere containing our number, and we want list to be the address of that block of memory. Well, when we come back from add, what's the value of list? It's null. Why? Because we pass by value. So nothing inside add can change the value of list when we get back to main. So our add function could add 1,000 nodes to this linked list, but when we get back to the main program, list is still null, and we've lost all that stuff that we added. So how do we reconcile that? Well, we can pass the address of list, because then we know that our function add can modify the value of list. But what does add look like now? So it still returns its integer flag. List is a struct node star. We're passing the address of list, so we're actually getting a pointer to a struct node. That's no fun. And then inside my add function, if I want to pull off a piece of this list, it's going to be something like star list, right? The thing it points to, arrow next, and so on. And that's no fun. And this just gets really kind of cumbersome. Now, an alternative is just have add return a struct node star. Pass it a struct node star. So now we're just getting our plain old list variable. It's just a good old struct node star. And our main program does something like this. Struct node star list, initialize it to null. And then when we want to add something, we do the following. We say list equals add list, comma number. So what happens? We call our plain old add function. We pass it the pointer to our first node, or possibly null, the number we want to add. But the add function returns a possibly different pointer to the first node of the list. And we save that in our list. And this basically allows us to change the pointer to the first node, or possibly null. But it's a special treatment, right? So the sentinel node takes care of all of that. It says we don't have to worry about that because the sentinel node is always there and it never changes. The problem with doing this is if our add function is returning a pointer to the beginning of the list, we can't get back that success variable, that 1 or 0 saying did we run out of memory or not. So now we have to have a third argument, success, which is going to be a pointer to an int. And when we call our add function, we have to pass the address of an integer and then check if if success is equal to 1 or 0. And that's kind of quirky. So Sentinel absolves all of these issues, absolves you from worrying about all of these issues, but it's not necessary. We can do all of this stuff and it'll work great. And when we get to trees, we'll actually do things without a Sentinel node. And so we'll see this kind of setup is what we're doing. We're passing in the beginning of a structure, but we're taking the return value from a function and possibly reassigning the beginning of the structure. And it's basically dealing with the case where we go from an empty list to a non-empty list. Same thing with delete. We might pass in the address of the first node, but if we're deleting the only node in the list, when we're done with delete, list should be null again. So we'd have to say list equals delete, list comma number. Okay, but we'll do this in our tree programs. Other quick comment. The struct nodes we've been working with, we have a data piece and we have a next piece, and our data piece has been an integer, but there's no reason it has to be an integer. It could be a character, it could be a double, it could be an array. It could be an array of characters, which is a string. It could be a structure. Right? So our struct node could have a data piece, which is a struct student record, and then a next piece, which is a struct node star. And it works exactly the same as the list we've been working with. It just happens that the data piece is not an int, it's a whatever, a struct student record. And we could say node arrow data dot some field in the student record. Or it could be a pointer to another struct node. And each node in our list could be something that has a data field which points to the sentinel of another linked list. And we could have a list of lists. And there's nothing wrong with that. And if you're thinking of this abstractly, if you're thinking of this in terms of these blocks pointing to each other, right, the code gets arbitrarily complex, but the abstract idea of what you're doing can be clear. So being able to think of these things abstractly, right, divorced from how we implement it in the C code, is really important. And when we get to trees, we're going to be just slinging nodes all over the place and deleting things and changing things that point to other things. And we can do that because we're going to think about it in terms of just these abstract nodes sitting somewhere pointing to one another. And then when we code it, that gets to be more of a headache. But if we understand the abstract notion, the coding is it's a fairly direct translation. All right, ran 5 seconds over, sorry. So we'll start talking about hashes tomorrow. And that'll give us a bit of a break from lists. And I'll post a list ODP tomorrow morning at 8.